Modem for digital phase modulation. This work was financed by the Norwegian Telecommunication Administration. The work we are going to report about here was implemented by Odd Trandem, assisted by Tore Skjøtskift, Hans Christian Rossing and Torleiv Maseng. Here we see a prototype of the equipment. The modulator of the equipment consists of a transversal filter with K coefficients. Note that this filter does not contain a digital integrator. Therefore, the modem is a phase modulator as opposed to a frequency modulator. These are the unit filtered pulses which last for 4.7 symbol intervals. The staircase function is generated by oversampling at 4 times a symbol duration. This emphasizes the digital integrator which has been removed in our implementation. In a FM system, A1 is 1. In our implementation, A1 is 0. Here we see the total modulator, which filters the input signal, and the filtered signals are fed to proms which perform cosine and sine conversion. These two signals constitute the X and the Y channels. The data pattern is generated by this unit. We can choose any sequence of a repertoire. The transmitter front plane is shown here. The sine and the cosine channels are the upper beams on the oscilloscope together with the input data. Less time resolution results in this figure. If the sine and the cosine are fed to an XY oscilloscope, this figure will appear if the bitrate is sufficiently low. Different data sequences will cause different segments of the unit circle to be illuminated. Here we see alternating ones and zeros and different other sequences with more ones and zeros. As the bitrate is increased, the circle will be more and more continuously illuminated. At 9.6 kilobit, the circle will be almost round, while at 16 kilobit, the effect of the anti-aliasing filters will cause the envelope to be non-constant. The 70 MHz carrier frequency is generated by this unit. Here we can see the effect of phase modulation, which corresponds to a time shift. The resulting envelope is almost constant. The power spectrum will be wider as the modulation increases. Tamed FM use a modulation index of 0.5, while in our implementation we have chosen H 1.2, indicated by the following figure. A modulation index of 1.2 corresponds exactly to that value which causes the residual carrier component to disappear, which is shown here. As the pulse duration increases, the residual carrier component will decrease. Note that at 2.5 the carrier component will again appear, which makes carrier recovery possible by doubling. The other periodic side lobe signals are practically zero, and any residual spectral line will be removed by the residual anti-aliasing filter. The power spectrum measured on a spectrum analyzer shown for plus minus 2 times the bit rate are shown here. In the practical implementation of the transmitter, the filter is implemented by a lookup table. We also see the anti-aliasing filters after AD conversion and coherent modulation to 920 MHz by a quadrature mixing system. Resulting in an almost constant envelope signal. Here we see the overall equipment, which contains equipment, the modem itself, the fading generator, the error analyzer, and several amplifiers and filters which make the power budget right. This is a general signal processor card. In the middle of this, we see the TMS 320 signal processor. The algorithms to be executed are, before program loading, resident in slow erasable PROM, which we see here. After program initiation, the program are converted to RAM, which is fast. There are 7 16-bit parallel input lines, and here we see the buffers. There are 8 time-multiplexed output lines. This card interfaces the error analyzer or the speech coder. This is a transmitter. The data is from the TMS processors are AD converted and then filtered through anti-aliasing filters with sharp flanges. The 70 MHz carrier frequency is added in phase and quadrature to produce a constant envelope signal. The input module of the receiver is a coherent phase lock loop which regenerates a carrier by first doubling the non-existing residual carrier component and then performing coherent demodulation, followed by AD conversion in phase and quadrature. When the coherent synchronism has been achieved, the circle will stop rotating. This is the phase trellis as it evolves from one particular state. The red curve is a received curve, and the green is a correct signal. All possible phase paths are shown with black color in this figure. Note the periodic structure of the trellis. Each part between the dotted lines correspond to one symbol duration. After some times, these will repeat. Here we see one such section. This is the periodic part of the phase trellis. The left hand is the input state and the output is on the right hand side. The two yellow lines corresponds to that choice the Viterbi algorithm has to do every symbol interval for every state in the trellis. Since after phase merger, the worst of the two paths will never win, this can be eliminated, and thereby is the number of states kept to a limited number. In this figure, we have 8 states corresponding to a pulse duration of 4 symbol intervals. There are in total 16 possible paths in this figure. At every state, an add, compare, select has to be performed. Calculation of metrics and selection of the best of the two. As an error signal is used the least Euclidean distance, which is a norm of the difference signal, integrated of the duration of a path in the trellis. This corresponds to a matched filter, which is performed for every phase path in the trellis. The matched filter is implemented as shown here. Eta corresponds to the oversampling ratio and is for the practical implementation chosen to be 8. The Viterbi decoder continuously selects the winning and the best path through the trellis. This is the input front end to the receiver. After a constant signal has been achieved, coherent modulation is performed and samples are collected by 8 times the symbol rate. Anti-aliasing filters are also used in the receiver. After DAD conversion, coherent demodulation is performed by a digital phase lock loop which performs tracking of the phase. The Viterbi decoder also contains circuits for calculating branch metrics, and everything is kept under control by the digital phase lock loop performing bit synchronization. The error signal to the digital phase lock loop carrying out bit timing is achieved by looking at the minimum accumulated metric. This is the front end module of the receiver. We can add noise by a hybrid This is in-phase and quadrature demodulation at 70 MHz, periodic side lobe suppression filters, which are analog, AD conversion, and circuits for clock control under control of DA converters. This is the receiver front end. Which contains mixers and AD converters, just described. At first, the signal is coherently demodulated in the digital phase lock loop. Bit timing is performed, and branch metric calculation is performed by 2 processor cards. Add, compare, select is done by 1 card, and then trace back is performed by the last card in this rack. Data interface module is here shown. Here we see the noise generator on an XY oscilloscope. The added noise at 6 and finally 2 dB signal to noise ratio is shown. Note that the noise has been filtered through a 16 kilobit analog filter, and at this noise level the error rate is around 10 to minus 2. The error rate is continuously measured on an error rate analyzer. This figure shows a comparison between various modulation techniques. Bit error rate along one axis and signal to noise ratio measured as energy per bit along the other. Tamed FM and Gaussian minimum shift keying are compared with our digital phase modulation implementation. At an error rate of 10 to minus 2, an energy per bit to noise ratio of 3 dB is required. Co-channel interference can be added. At 0 dB carrier to interference ratio, this is the resulting XY oscilloscope diagram. At an bit error rate of 10 to minus 2, co-channel interference ratio of 2 dB can be sustained. In this figure, energy per bit to noise ratio is shown along the y-axis, while co-channel interference is shown on the x-axis. At a constant error rate of 10 to minus 2, 2 different modems are compared. The yellow one is generalized tamed frequency modulation, while our implementation of DPM is shown in the red curve. Fading of the desired signal can be implemented by using a fading simulator. At 10 km per hour, the resulting signal looks like this. At 50 km per hour, this is the result. At 90 km per hour, this is the resulting XY oscilloscope diagram. The result of fading is represented in this figure at various speeds of the vehicle. In a practical scenario, The stationary performance shown in the left-hand curve and the rarely fading curves on the right-hand side represent the bound between which a practical system is likely to be found. We wish to thank Jan Audestad and Bjørn Løken for their continuous support and encouragement throughout this project.